Hello, I'm Jacob Fritsky, a junior at IUP, and for USOR, I did the synthesis of chitin nickel alginate beads for removal of brilliant green from wastewater under the faculty supervisors Dr. Andrada Makananu and Dr. Jacques Njomu. Our goal was to create a filter that is renewable, can easily be separated from water, can be regenerated after use, and efficiently removes contaminants from wastewater. Why did we use chitin and nickel? Chitin is a renewable resource that can be found from animals such as crabs and shellfish. Chitin has also been observed to have antimicrobial properties. Nickel has magnetic properties. That way it can attract metals such as iron and cobalt that are also magnetic. How did we create the chitin nickel alginate beads? We first started with a snail shell and ground it with a mortar and pestle so it would react better with hydrochloric acid. We filtered off the hydrochloric acid and washed it with distilled water to get rid of any extra hydrochloric acid. We then deprotonated any proteins with sodium hydroxide and filtered and washed that with distilled water to remove any excess sodium hydroxide, and then impregnated it with nickel ions. We then filtered that off to remove any excess nickel and washed it with ethanol and calcinated it in an oven. After calcination, we rinsed and ground the material. We then combined the material with sodium alginate. That way it can form polymer beads. We used ethanol to activate the sodium alginate, added distilled water until it was a slurry, and then added that dropwise to calcium chloride so that way it would form the beads when calcium chloride reacted with the sodium alginate. Our final product were chitin nickel alginate beads. To characterize our material, we used the FTIR, the SEM, and the EDS. Our first FTIR shows snail shell powder and chitin nickel powder. In the chitin nickel powder, there is oxygen-hydrogen bonds, as well as carbon double oxygen bonds, carbon-hydrogen bonds, and nitrogen-hydrogen bonds. All are similar to the snail shell powder except for the oxygen-hydrogen bonds, which are present due to the nickel in the chitin nickel powder. For our second FTIR, we have chitin nickel alginate before and after it absorbed brilliant green. There are carboxylate salts in this FTIR because the alginate is present. The SEM for the snail shell powder and chitin nickel powder both show that they are homogeneous without any special patterns. The EDS shows that our process was successful because the chitin nickel powder has nickel present in it, whereas the snail shell powder does not have nickel present. For our working conditions, we did batch and column runs. For our batch runs, we had concentrations ranging from 50 milligrams per liter to 400 milligrams per liter of brilliant green, and temperatures ranging from 25 degrees Celsius to 50 degrees Celsius. This allowed us to find the optimal conditions for filtering that we would later use in the columns. The column runs allow us to gain data that would hopefully allow us to scale up to industrial applications. We ran 2 samples so far, concentrations at 100 milligrams per liter and 300 milligrams per liter. The beads were reused in each batch. For desorption, we used a concentration of 40% ethanol and 60% water to regenerate the beads at a temperature of 70 degrees Celsius. We are currently gaining more data for these runs. For our results, we have snail shell powder alginate beads and chitin nickel alginate beads. The chitin nickel alginate beads show that the modifications due to nickel significantly improve the adsorption of brilliant green compared to the snail shell powder alginate beads. Here we have different concentrations of brilliant green, all reaching equilibrium after 250 minutes, with the exception of 50 milligrams per liter of brilliant green, which reached equilibrium in 150 minutes. This shows that the chitin nickel alginate beads can work under high concentrations of dye. Here is the data for concentration, temperature, absorption capacity, and efficiency. We reached an absorption capacity of 69.76 milligrams per gram and a high efficiency of 97%, with optimal conditions being 200 milligrams per liter of brilliant green at 40 degrees Celsius, which reached an efficiency of 97%. Here is the breakthrough curve of our column at 300 milligrams of brilliant green per liter. At the beginning, there is a low concentration coming out. This is because the chitin nickel alginate beads had not yet absorbed the brilliant green, leaving a high surface area on these beads. As the time went on, the beads absorbed more and more brilliant green until it reached its max capacity, at which the concentration coming out of the column was equal to the concentration that was going into the column. From our results, we have concluded that modifying snail shell powder with nickel has improved the absorption of brilliant green. Chitin nickel alginate beads show promise in removing catatonic dyes. The chitin nickel alginate beads are also stable and reusable, and they show the possibility of being used to remove harmful dyes that could end up in the environment. Thank you for watching my presentation.